Hey everyone, Fraser here. So I'm going to try a new experiment now, which is to do a QA based on the newsletter. So everyone who is receiving the email newsletter, if you're getting this and you're reading the newsletter and some question pops into your brain about the news or just like space news in general, then just reply to the email when you get it, and I will gather a bunch of questions up and I'll answer them here and then make it available to everyone in the newsletter the week after that. So I've got a bunch of questions that came from people, and I've queued them all up. So let's get into the questions. All right, so the first question: I like stargazing. Can you suggest any app for this? Suhas. Absolutely. So when I do like plan out my stargazing, the main app that I like to use, actually I do it on the computer, is Stellarium, and that was the screen share that I was showing you right now. And Stellarium is a completely free software. You can run it on your computer. It shows you sort of where everything is in the night sky, and you can even control your telescope. Like I could control this telescope behind me with Stellarium. So it's pretty great. Now they do have an Android version as well. I think it costs about $3, but Stellarium is fantastic. That's the only one that I know of. But if other people have used other stargazing software on their mobile phones, please let me know. I would love to know some ideas on what you like. All right, next question. So when the USSR and the USA were testing the viability of sending humans into Earth orbit, they first sent animals, monkeys, dogs, at least one cat, to see what would happen to them. Will animals be used again for testing, or is this deemed not necessary now? When animals were being used originally at the beginning of the space age, like with Ham the chimp and like the dog, it was really, they had no idea what effect spaceflight was going to have on human physiology. They just didn't know. Would we explode? Would we pop? Would we melt? Would we be able to eat, breathe, do all the things that animals can do in space? Now they had tested a bunch of that stuff on Earth in vacuum chambers and low gravity, but to test low gravity, you really have to be out in space to be able to do it. So that was why they did a lot of the early testing. Now, that said, there have been animal tests that have been done on various missions. There was a bunch done on the space shuttle, and there's some been on the International Space Station, testing things like, how do spiders spin their web in zero gravity, or how do fish operate in, when they're in microgravity. And so you can anticipate that this is going to happen into the future. There was one really cool experiment that never got tested, which was to put a bunch of mice, say, on the space station, and then have them be in a rotating kind of little mini mouse space station to see if they survived better in sort of simulated artificial gravity than regular gravity. But at this point, the next big question is what happens to human beings over the long term. We know that a human being like, say, Scott Kelly, when he was on board the International Space Station, he had various things happen to his body over the course of a year. So that's fairly well known at this point, but we don't know what's going to happen after, 10 years, 20 years, a whole lifetime. And so probably as we explore farther out into space, we'll probably do more experiments with animals to try and find out what's going to happen and try to predict what the impacts are going to be on human beings. All right, next question. All right, this comes from Cirilio. Where do interstellar voids start and end? Is the space between Andromeda and the Milky Way a void? If no, why not? So this is this idea of cosmic voids, and when you look at the large scale structure of the universe from sort of the widest vantage point, the whole universe looks like sort of the sponge where there's these huge walls, and the gravity has pulled together all of these galaxy clusters together, and then in between these sort of areas where all the galaxies are these giant voids. And a void really is more a question of just the density of material in that region. So if you've got a place like around the Milky Way or in our own supercluster, that is considered one of the areas that's not a void, and then you've got the areas in between. But you can still have stars and even galaxies in these voids in between. It's just that you're less likely to have them. The total amount that you're going to see is going to be lower. So you wouldn't necessarily consider the space in between, say, Andromeda and the Milky Way to be a void in that sort of in these giant super voids that are in between galaxy clusters, but it's definitely mostly empty space. But even in that space, there's going to be hydrogen atoms, there's going to be various particles in between, and possibly the occasional star. It's just that stars are more densely collected into galaxies and galaxy clusters and things like that. All right, next question. Ed asks, one issue that's bothered me for a while. I understand why a bright star would appear larger in size from a photo taken on the surface of the Earth. The star is essentially a bright point, but the atmosphere would scatter the light to show it as a larger object. Can you explain why the photos taken by Hubble also show bright stars larger in size than dimmer stars? Yeah, so when when telescopes like Hubble, they're equipped with a charged coupled device, a CCD, and it is a way of capturing the photons that are coming from some distant object, like stars, star clusters, things like that. And the way these CCDs are, they're like a grid, and as the photons come in, they can overflow the one part of the CCD into the parts that are around it. I think it's called blooming, but anyway, because it's oversaturation, and so you will get the one detector has filled up with photons, and then the ones around it are starting to catch photons. And so that will make this object look bigger, more bright in the photograph than if, as you said, if it was just like capturing single photons and could capture an unlimited number of photons, you wouldn't see these sizes in these pictures like we do. So like everything with the photographs that we see from space, you're seeing what happens with a telescope that is gathering photons onto a camera for a long, long time. If we could go out into space and see nebulae and galaxies and things like that with our own meat cameras, they wouldn't look the same. They wouldn't have that same, those colors, all of that. So a lot of what we see in all of the pictures are really due to the fact that a telescope can gather a lot of light, and a camera can sort of absorb those photons and expose them for very long periods of time, days sometimes. So that's why we see that. All right, next question. All right. Recent articles said that the moon is receding a little over an inch a year. Will the moon eventually pick up speed in its drift away from Earth and go elsewhere in the solar system, perhaps outside of it? So the moon is drifting away from the Earth, and the reason the moon is doing this is because the moon and the Earth are tidally locked, or the moon is tidally locked to the Earth. And so what happens is the Earth has like handles on it, right? So it's a little wider in parts than it is in other parts. And so as the moon passes along over the Earth, it kind of grabs onto those gravity handles and slightly slows down the rotation of the Earth. And what this does to compensate, because you have to sort of conserve all of the momentum in the system, is it causes the moon to drift outward a tiny little bit. And so we already stopped the rotation of the moon from the Earth's perspective, and now the moon is trying to stop the Earth from rotating from its perspective. And eventually, like 50 billion years from now, I forget the exact number, the Earth and the moon will finally have locked to each other. They will both be facing in this, towards each other, and they will no longer drift apart. So the moon isn't going to drift out into the solar system. The moon and the Earth will eventually drift to a point that they are locked to each other, and then they'll stop that outward motion. Of course, 50 billion years from now is a lot longer than, the sun is going to survive, the Milky Way and Andromeda will have collided. So it's a very long time in the future, and you don't really have to worry about it. All right, next question. I see a lot of talk about reducing cost to orbit, but what has SpaceX actually accomplished in that regard? For a low Earth orbit of similar inclination, what do they charge per kilogram versus Lockheed, Europeans, and Russians? I don't know the exact prices for all of those, and a lot of the times it's a negotiation with the rocket launch company. But in general, if you want to buy a launch on a Falcon 9 rocket, it's going to cost you about $65 million. And if you want to buy a launch on a Falcon Heavy, it's going to cost you about $90 million. The price per kilogram on a Falcon 9 is, I think, about $5,000 per kilogram. And the price on the Falcon Heavy is about $1,700 per kilogram. And so you can compare that to a similar launch on, say, a United Launch Alliance rocket like an Atlas or a Delta, and you're going to be paying about $300 million or maybe more. So in theory, the costs from from SpaceX are significantly cheaper than the costs that come from the traditional rocket companies right now. And same with the Europeans. I'm not sure what the Russian prices are, but SpaceX is significantly cheaper. That said, SpaceX provides cargo launches to the International Space Station, and their prices are pretty expensive, and they've actually gone up this year with the sort of the next round of launches. So, but yeah, if you want to launch some stuff into space, pick a SpaceX rocket. They're pretty cheap. We'll see what happens when Blue Origins starts to launch and offers fairly competitive prices to them. All right, next question. All right. So Raphael asks, what physical force prevents the Voyager 1 and 2 to reach the speed at which the entire solar system is moving across the Milky Way galaxy? I mean, there's no drag from particles in space. Is it only the sun's gravity effect? Right. So the Voyager spacecraft, which were launched from Earth, used a bunch of tricks to get out into the outer solar system at the velocity that they're going. And I think right now they're going about 17 kilometers per second, and the escape velocity of the solar system is about 16.5 kilometers per second. So they are going faster than the escape velocity of the entire solar system. And what that means is that they are going to keep going forever, right? They are not going to be stuck inside the solar system. They're gone. Our gift to the Milky Way. But that said, there is no drag out in space. There's nothing that's going to slow them down, and they're just going to keep on drifting. And I did the math fairly recently that over the next billion years or so, they'll be able to travel about half the width of the Milky Way. So they could get, say, from here to about the same spot, the same distance from the galactic core. They could make it out to the outskirts of the Milky Way. So they're going to drift, and like a billion years is expected for how long. They're not going to be still operational, but the golden records are still going to be there. They'll be worn down by space dust, but they could still be potentially found by a future alien civilization and studied. So that is our gift, like I said, to the Milky Way. All right, next question. What are your thoughts on the possibilities of intergalactic von Neumann probes? I know something like that, like half all the stars in the universe are intergalactic and could conceivably serve as waypoints for probes as they refuel and make more of themselves to spread from galaxy to galaxy. If possible, this would radically increase the number of star systems that you have to account for in your Fermi equation and make it all more confusing to why we haven't detected any yet. Yeah, absolutely. The Fermi paradox, of course, is this idea that we look out into space in all directions, and the universe is old, and the universe is big, and the conditions for life have been around in the universe for billions and billions of years, far older than the age of the Earth and the Sun, and especially human civilization. And so there could have been many places where life could have evolved. That said, you can imagine that an alien civilization could show up on any one of those planets in the Milky Way, build self-replicating robots, and then they could use them to explore. Send one robot to one star, it replicates, sends 2 robots to 2 other stars, they replicate. And there's a great book called I Am Legion, We Are Bob, at the Bobiverse books, and they really explain sort of how von Neumann probes would operate, and kind of how when you have access to the resources of a galaxy and you have the ability to replicate your spacecraft, you can make many, many more copies. And this is one of the things why I personally find most explanations of the Fermi paradox a little underwhelming, because this idea that anywhere you started, you could colonize the entire Milky Way. And so this question is, could you colonize other galaxies? And the answer is absolutely. And so, I mean, sure, you could end up being on some star, some rogue star that's on its way out of the Milky Way, but you kind of have to reach the velocity of that star to be able to catch up to it. Or you were on it when it got hit by a supernova or kicked out of a supermassive black hole, which is a pretty terrible event. So you probably wouldn't be able to survive that. But there could be gravitational slingshots that you could eventually make your way out into deep space. And the reality is that as long as the galaxies aren't moving away from you at faster than the speed of light, you could eventually reach other galaxies and colonize those as well. And so this is sort of one of this, and what this question is exactly saying is that it makes it a little weirder that we look out into space and we don't see aliens out there colonizing entire galaxies. So it just makes the Fermi paradox even more paradoxical. Where are they? Where are all the aliens? Why are we alone? Why do we seem to be alone? And there's no easy answer to it. So, all right, well, those are all the questions that I had today. Just 8 questions. So thanks, everyone, for sending them in. This was a lot of fun. At any point, if you are reading through my email newsletter and you've got a question that you want me to include in this mini show, just reply to the newsletter and it'll come into my email, and I'll gather a bunch of them up and I will answer them here. All right, we will see you all next week. And if you're watching this somehow and you haven't subscribed to my newsletter, go to universetoday.com/newsletter and sign up. All right, we'll see you next week.